there is one appeal. All the delegates has provided with the kits and writing pad is also there. So if anybody has got any doubt, any questions, they can very well write on their writing pad and pass on that sheet to organizers. So all your queries will be answered. Are in seismic design of reinforced concrete and steel structures. He has co-authored numerous publications with Professor MURTY, such as Earthquake Behavior of Buildings and Introduction of Earthquake Protection of Non-Structural Elements in the Buildings. So with a very short and crisp introduction, I request Goswami sir to begin with the lecture.
A very good morning to all of you. The voice is a little choked, but I hope it's okay and you will be able to bear with me. First of all, it's an honor to be here and in this institute, of course, and I see a lot of senior people here. I sincerely thank you all for taking time on a working day and be here for this. It just shows that not just we, some of us, but all of us are very passionately interested about this whole topic, right? And so this is going to be an occasion for all of us to think about this whole profession that we are in, particularly with regard to two important aspects. One is, of course, we are going to talk about IS 456, and I think that is something more than the earthquake engineering course. It's the 456 which matters a lot. It's the bread and butter, roti chawal, whatever we call it, for all of us. So that excitement we will have post-lunch session. But before that, the earthquake problem that we have, let us try to understand what are the issues, main issues here, and then we would also love to, get feedback and your opinion and your suggestions on that, right? So I'm only going to present the thinking process that is currently going on, so that you can pitch in and then give your ideas also. If I had the opportunity to ask all of you even before starting anything, what is that single question that you have on 1893? 1893 part 1 and part 2 were under wide circulation some time back, so all of you have seen that. So what would that one question be? If you are allowed to ask one question, what would that question be? Well, I guess you would have some question related to the hazard part. So I'm going to start with that and talk about the hazard part. But more interestingly, what is going to happen is in future is that when we talk about earthquake engineering, earthquake-based design and related standards, there are a lot of standards that is currently there. As a student, it becomes difficult, and even as a practicing engineer, it becomes difficult to remember all this. So we are going to simplify the whole thing, and there is a lot of harmonization process that is underway. So we are going to talk about only 3 verticals, which is IS 1893, 13920 and 139, so that it becomes simpler, and then talk about the whole setup, present the setup. The first thing is, we are talking about revision of IS 1893 part 1. Now part 1, as it stands today, has 2 parts to it. One is the general provision and the things, which now is going to only stay as the general provisions for earthquake-based design. So what are the things? So the original mandate, after a lot of deliberations in BIS, was that let us simplify and harmonize our earthquake-based design codes. So as I said, when we design any new structure, we have to look at two components. One is the demand, which is the hazard, seismic hazard part. The other is to provide capacity for that. So the idea is to have 1890 vertical providing demands for design of all these different types of structures. And then 1390 to provide provisions and specifications so that these structures can be designed to have requisite capacity. So that is the only two verticals, and that is where we are going to have different parts for each of these structures. Now when we talk about existing structures, right? So there we have to do assessment, and there are two parts, two different components are required. One is of course the demand for which the old structure has to be reassessed, and then the process of assessment and then coming up with strategies for repair, the decision making process which will lead us to repair and repair. So that vertical is one structure. And so if we now look at these three, this is where we are going to put all the different types of structures here, and then we'll have a standard format. So this is the whole agenda that DIS gave us, and based on which 1890 is now getting revised. The proposed draft was circulated, and this is what we are going to discuss right now first. What is the motivation? Of course, we have had 1893 for last 5 decades, but then we also have had surprise earthquakes in India. We have had lives lost and properties lost in many of these earthquakes. But the most interesting thing is that we have about more than 60% in fact today population living in the higher zones, higher seismic zones. And the surprise events that we have had were significantly higher than what we had originally estimated, or even today we believe these regions can provide. So as and when these different Director VJTI mentioned about Hillary, so and there was Jabalpur, and starting from Koina and so on and so forth. So as and when all these earthquakes kept on occurring, we kept on updating our zone map and also the zone and the zone coefficients. And so it is a process that has been happening for many years. It's not a new process. But today, again, so in 2024, the work started a little earlier, but today again we are at a crossroad where we definitely have a need to update this once more, and that is what we are going to discuss. But the challenge in all this is that there is insufficient data, really recorded data. When I say data, I mean recorded data of past earthquakes, and then because of which also there has been an underestimation of the earthquake hazard in the past. And obviously, why do we have insufficient recorded data? Because we have insufficient instruments in the country. Not every part of the country is well instrumented as we would love it to be. And I'll show you the statistics also. So, as a first cut, if you therefore look at what is the trend, right? You get to see that in reality, the peak horizontal ground acceleration that has been recorded or interpreted from different intensity measures that has happened due to real earthquakes that has happened along major similar tectonic regions, you will see that these are somewhere close to 1G. And these are all recorded data. So there's no bias in that per se, right? And obviously it fits well with the correlation that we have, generally accepted correlations. So the point is that when we say that the maximum earthquake ground acceleration can be 0.1, 0.2, 0.3, that gives us the first indication that there is a need to look deeper into the whole process, right? And then, so that is the whole idea, and that is where we thought, it was felt that we need to take seismic hazard analysis for the country in a much deeper way, and that is where the whole work began. So our design code values of 0.1 to 0.2, 0.3 did not seem okay in terms of things that have been recorded in the past. And also, our own experiences in the country, not just from other parts of the world, our own world, the country experiences tell us that there is need. So therefore, this revision is coming up, and these are the different parts of IS 1893 Part 1 that is going to be there. And I'm going to focus on this item number 6, the serial number 6, which is the earthquake hazard, which is the major part. So what is the major change? The major change is in the hazard and the way the hazard is estimated. Now, what is going to happen is, you have already seen the draft, so you know that the hazard levels are different, and if you compare a certain value of Z value, for instance, you will see that there is a difference. And then the question automatically that comes to mind is, how come there is such a, so much of change? Well, it has not happened overnight. Honestly speaking, there has been a very systematic effort towards this made by various people. And if you look at these 3 documents published, with support from NDMA, this work is more than decade old. And every time there has been refinement, and I'm sure some of you, who are sitting here have been part of various committees over the years, either reviewing such work or providing inputs to such work, and so on and so forth. And so, after all these years of very rigorous study, today we are at a level where we are talking about a new seismic hazard assessment of India, where a probabilistic seismic hazard analysis has been carried out. Now, here, of course, this is not the end. There are multiple levels that can be done. Those who work in this area. To begin with, we have been using isosysmals of past earthquakes to determine our zones. You saw the transition, how the seismic zone map of India changed. Those were essentially based on the isosysmals of the past events. Then one can do a deterministic analysis with mapped faults, which was also considered. And today we are at a stage of probabilistic analysis. We need more instruments, we need more instrumented data, we need ground motion prediction equations to develop based on recorded data from the Indian landmass. And finally, we have a way to go, where particularly even today, we are actually not considering near fault effects, which is a significant thing that is going to happen, come up in the near future. Because India, if you see the tectonic feature of our country, we have a long thrust convergent plate boundary, and that is where these near fault effects can be significant. So we will reach there. But for the time being, how is this hazard assessment done? It is made up of 2 parts. One is the deterministic part, and the other is the probabilistic part. I'm not going to go into the details of all this, but essentially there is a data, actual recorded data which is used, and then there is, based on that, the actual fault map is used, and then using a statistical method, this analysis is carried out. So the hazard that we are going to see is an outcome is basically a hybrid kind of a thing, where both deterministic as well as state-of-the-art probabilistic seismic hazard analysis methods are used to come up with that. What is the output? The output that we got is that we get some numbers of peak horizontal ground accelerations for certain return periods of events. So this is a new concept that we are going to see in the seismic event. Right? Earlier we had only what we know as zone factor Z values. But that Z value did not come with the concept of return period. So what is this return period? The return period is essentially a statistical number, so as to say that the recurrence of such size of earthquake is so many years. Now it does not mean, for instance, if we talk about an earthquake of 2,475 years, it does not mean that that earthquake will occur only after 2,400 years. It can happen right now, it can happen tomorrow, or it may not even happen, right? So that is the thing that we must keep in mind. Now the question is why this number, magic number of 2475, 975 and all this. We will see why it comes in this particular fashion. Essentially, when we design, we always take risk, consider some probability of that particular level of demand to be exceeded, what we call as probability of exceedance. So essentially, if we consider a regular structure, a normal structure to have a design life of 50 years, and then if we want to say, okay, I will consider 10% probability of exceedance. That means whatever value I consider in my design, there is a 10% chance that that's going to be exceeded. If we make that statement, it essentially means we should look at events that have a return period of around 475 years, and so on. So what you see here, these numbers essentially mean that. And these are generally very accepted norms used worldwide. So we are not, doing anything new. It is something very standard process in doing earthquake-based design. So that is how these numbers come in. Now the only question that is left is, so therefore corresponding to each of these return periods, what are those Z values that we finally get based on our seismicity, the seismicity in different parts of India that we have. So that is the whole process. And that process begins with the whole seismic setup of the country. So essentially, if you look at it, we have a huge the sediment belt, we have the convergent belt, plate boundary, and we have the river deltas, and we have the Indian shield region, and then we have a Eurasian plate. So essentially, the Indian plate is colliding with the Eurasian plate. So the first step, as I said, the entire country is discretized into small regions. About 60,000 grid points were used to discretize the entire country. About 68,000 total events were considered. These are past earthquakes. There were about 26 events which had magnitude greater than 8, and you can see the epicenters marked on this. For each of these now, when we talk about the entire country being discretized into this, there are three broad regions, seismic regions which were considered. As you can see, the stable continental region, the active region, and the northeast region. And then there are enough literature and research available that basically demarcates the seismicity of each of these regions to be slightly different from each other. So for each of these, there are certain ground motion prediction equations that were developed, and for that different kind of weightage and logic tree concepts were used. And then once that is done, then finally the entire country was again demarcated into 33 seismic source zones. So, and you can see it also includes the, a region in Tibet and so on and so forth. So that we just don't consider the seismicity within the country, but what can come, of course, the political earthquakes do not understand political borders. So, that is where it was important to consider that also. And we, there were some 1831 faults which were considered, including 42 in Sri Lanka. Now, once these seismic zones are demarcated, the basic seismicity of each of these zones were studied. So, the recurrence relations for each of these 33 zones were developed, statistical data were generated, and finally, the probabilistic hazard assessment process got initiated, right? So, in this thing, the uncertainties of earthquakes per se, and then the mathematical uncertainty that is always going to be there in the mathematical modeling, our interpretation of that was also considered. And finally, what we were trying to get was the peak ground acceleration, peak ground velocity, peak ground displacement, contour ratios, contours for the entire country. Now, the interesting part is, worldwide, this whole process of hazard assessment is generally done for 2,475-year written period. Why? Because for 50-year, for structures with 50-year design life, considering 2475-year written period even is equivalent to saying that, making a statement that we are going to consider 2% probability of accidents for the maximum earthquake that we are going to consider for purpose of structural safety. So that is the standard practice, and that is precisely what we have also used here. Now, obviously, when you do such statistical study, you will get very, I'll show you the real contours you will have. So then there are processes that are involved in terms of smoothing the data and so on and so forth. So standard processes were done, considering background seismicity also. So these elliptical smoothing and circular smoothing, all these things were done. And finally, we were for every region, the response spectra were developed. Now, these spectra, for instance, you can see the Uttarkashi, Nepal main event, and so on and so forth. So there are already recorded data, and then these spectra were matched, or rather validation was done of the model to see that yes, things are reasonable in that sense. So we got contours like this for peak ground acceleration across the whole country. But then obviously you can see that there are too many contours, too many local bends, and so on and so forth, right? Now, this analysis, the hazard analysis, is generally done at the bedrock level, and this is something that is significant that has happened in our case. So the spectral acceleration levels were checked at different natural period, right? And then finally, once that was done, then when we looked at those numbers, of course, I mean, we could have stopped at that level. But then there was a need felt to see that we also do a standard deterministic hazard assessment and see that none of the numbers that we have got are way off than general understanding of the seismicity of the region. So that was also carried out. So for each of the source zones, the largest event was considered, taken into consideration, and then again a deterministic seismic hazard assessment was done. The country was again demarcated into different regions. About same 60,000 grid points were taken, and then finally we got a deterministic seismic hazard analysis based contour. At this stage, what was decided was finally that this two analysis results that we have got, now we need to put them together and get the final one. So this is what we have as deterministic plus probabilistic. So it is the maximum of deterministic and probabilistic earthquake hazard assessment contour. So what it does is that it gives a higher level of confidence in the final result. And then the most important thing that I mentioned, that all the standard hazard assessment analysis is generally done at the bedrock level. This is where a significant departure was made, and we wanted to get the spectra at the soil level. And so we looked at the entire geological setting of the country also, not just the tectonic setting but the geological setting. And accordingly, you can see these amplification factors. Of course, there were amplification and local pockets were there where there were de-amplification and so on. So again, statistically it was handled. But essentially, for different types of geological setting, you can see different levels of amplifications were seen through analysis. And that was considered to finally come up with peak ground acceleration at the surface of the earth. This is a significant step you will not find in many cases, right? So finally, once everything was done, a contour would have looked something like this, which is very hard to use for daily design activity. And so the next process of smoothing it out and finally coming to this zone map, that process got started. And of course, there were standard processes, procedures which are there as to how to do the smoothing, how to handle. So essentially, some of the key things that I can mention that were taken care of is that no major CT falls on the boundary of a zone, of two zones. If there is an urban setting, it was made sure that the boundary of a zone goes beyond a certain kilometer and they don't fall exactly, and things like that. We looked at the population of each major town and city and took a decision on where to put that. These local modifications were done, but broadly it was a very systematically carried out scientific analysis based thing that happened. So now if we put back all the recorded events and epicenters on top of the zone map, this is the picture. You can see that yes, there are a few smaller islands that you will see, but those are inevitable, you can see. And the most important picture I think for all of us to remember is the superposition of the zone map with the fault, the active fault map. And if you look at this, you will have lot more confidence in the zone map. So the zone map was done. Now the final thing is, when you also had looked at the zone map, you also looked at the instrumentation that we have in the country, because the whole process relied heavily on past data, right? And of course, we did not have full record of all motions because this is very recent earthquakes only we have data. For the earlier ones, we had to rely on other sources. But the interesting thing that you would be interested in knowing is that today in India, if we look at, we have one instrument per 21,000 square kilometer, on an average. Of course, there are regions in the northern, thing where we have a little more density. But if you look at countries like US, Japan, or even Taiwan, of course, it's a smaller island nation. There, they have one instrument per 72 square kilometer. Look at the difference in instrumentation that we have. And this is significant because if we have good quality data, obviously we will have a lot more confidence in our hazard assessment results. But nonetheless, a tremendous job was done over the last 10 years or more than 10 years to finally come up with this particular zone map. And so essentially now if you see here, earlier we used to have 4 zones, 2, 3, 4, 5. Now we have 2, 3, 4, 5, 6. If you are wondering what happened to zone 1, the idea was that, of course, when we began, we also had a zone 0, right? We had a zone 0 and we had zone 1. It gives a feeling that these regions are non-seismic. But if you remember the fault map, we have active faults almost everywhere in the country. So it was not to give or convey that sense of, thing that, okay, this part of the country is non-seismic. No, there's nothing. So that is why we continued with, starting with zone 2. But essentially, if you see, the entire thrust boundary is zone 6 now. The dark chocolate color that you see, starting from Kashmir, Jammu and Kashmir to the northeast, and most importantly, Andaman and Nicobar. We are going to have a lot of strategic facilities coming up there, and it's a very, very important place to take care. Right? So, what are the implications of this whole work that has happened over the last decade or so? So as I said, what you are seeing is the output of a kind of a hybrid method where this deterministic and probabilistic hazard analysis either has been used in tandem, and then finally we have this zone map and thing. Now, for practicing engineers, the important part is, okay, zone map is the first part. The second part is what is the zone factor. Then the zone factor values, if you see, now these are the values of acceleration, the horizontal ground acceleration in each of these zones that you see. Now obviously a quick comparison of these numbers with what we today use will obviously give a surprise. And what happened? I mean, how come 0.36 become 0.75, right? But then, as I said, we need to understand how we are going to use this. The interpretation is important, and these values are those corresponding to 475-year return period events. And how does that come into the design aspect is what we are going to also discuss in the next part of it. But before that, some important GK kind of thing. If we see today, if you look at this table on the right hand side, right, we have in seismic zone 2, we are having around 28-30%, I will say 30% of the country is still in seismic zone 2. But then seismic zone 3 has earlier been about 33%, and even today is 34%. And this is where many of the major cities and towns are, right? So that is something that we need to take care. But then what we have is the remaining 1/3 is basically seismic zone 4, 5, 6. And this is where the actual action is. So if you think of it this way, that it's 1/3, 1/3, 1/3 primarily in terms of land area, right? Where we have regions of real high seismicity, and then the middle 1/3 is where all the important towns and cities are, all the major infrastructure development is, with reasonable seismicity. And then we have seismic zone 2 where, yes, the seismicity level is relatively lower, but we cannot still declare it, insignificant. So that is the big, macro thing that we can all take back today from this whole thing. But the other important aspect is, systematically done for different types of soil with different, VS values, and all that was done. The other important aspect, talking of infrastructure, is that a lot of our infrastructure, while all this is in terms of horizontal ground acceleration, a lot of these infrastructure like piping and all also needs vertical ground acceleration. That is also important. Until now, we have been using a fraction of the horizontal ground acceleration in our design. So since right from scratch, a very rigorous analysis was carried out, So it was time to systematically look at and develop vertical ground acceleration spectra also. And so you will see that this particular spectra, this variation is given. It's not a constant fraction, but there is a variation that you will find coming up there also. So again, this is a new or addition that we will find in 1893 part 1. Again, statistically these were all tested for each of those 33 seismic zones. They were developed and so on and so forth. All the standard processes were followed. And so finally this is the horizontal ground acceleration spectrum that you will find. And you will see that there is a small portion which is here up to 0.01. Then there is a linearly ascending portion with up to an amplification of 2.5. Sorry. And then of course we have the plateau part, and then there is one drop up to 6 seconds, and the spectrum is going to be given up to 10 seconds. Now 10 seconds obviously is not for regular structures, buildings and so on and so forth, but there are flexible structures like pipelines and so on and so forth which can have longer natural period. So the scope is now the spectrum will be given up to 10 seconds. And also the issue of damping is going to come back. So there are possible, for different values of damping it can be modified. Now let us come to these values that we saw of Z. This 0.15, 0.3, 0.45, 0.6, 0.75. These are the values to remember. But as I have been saying, these are values corresponding to 2475. So what happens if we consider, let's understand this, for I see a lot of younger people, and probably, I don't know, students are also probably here, so just for their thing. So event which has a higher return period is a bigger event. An event which has a smaller return period, that means it occurs more frequently, is a smaller event, right? Very infrequent event means it's a very rare, very big event. So there is a trend, there is a natural trend that if a bigger event is this, a smaller event size, how does that variation work? So when you look at events of smaller return period like 975 year, 475 year and so on and so forth, if we have got the value for 2475 year return period, it is possible to step back and get these values and also go beyond. So that is how the Z values, the same Z values, zone factors for different return periods can be obtained. Now this again was tested, and this follows what we have, and what was ensured is that this follows the global trend also, right? Of course you can see that the numbers are rounded. You will never get, when you do such rigorous analysis, you will never get exactly rounded off 0.15, 0.3 and perfect. So though these numbers are rounded, but the trend is perfectly in place, in order. And so we get these lower values of Z. Now the important point to remember is that all structures we distinguish between the relative importance of failure of a structure. So for instance, if it is a very critical infrastructure, let's say your main bridge versus a regular building. If that building gets damaged versus if that bridge gets damaged, the implications are going to be very, very different, right? So therefore, you can think of it this way, that you would be okay to take little higher risk while designing that simple building, but you would definitely not like to take higher risk when you are designing that critical infrastructure. So therefore, the statement that is made is that regular normal structures can be designed for 475-year return period events. Important structures can be designed for 975-year return period events, and only the lifeline critical structures can be designed for 2475 years. There are another category of special structures which can be designed for even higher return period events, right? So that is the whole idea. Now, what is normal, what is important, what is lifeline? Remember that table of different parts. So for buildings, the particular group will define which type of building they will call as normal, which type of buildings they will call as important, and so on. Similarly, the bridge will define their normal, important, and critical lifeline bridges. Water tanks, they will define which size, which type of water tanks will be called normal water tank, which type will be called important water tank, which group will be called, lifeline, critical and lifeline water tank, and so on and so forth. So that is the general strategy that is going to be adopted. So how do we do the design? We have got the zone map, we have got the appropriate Z value we need to keep depending on the structure, the type of structure. And then obviously we have to go to the design spectrum. Based on the natural period of the structure, we get the acceleration. Right now, today we call it SA by G value. So that acceleration coefficient we are going to get similarly, and that will give us the horizontal acceleration, design acceleration coefficient. And these values, these things will come in parts 2 to 11, where part 2 is going to be on buildings, 3 on liquid retaining structures, 4 on bridges, retaining wall is probably going to go away into a separate part, 5 is going to be industrial structure. So you can see there is going to be a renumbering also, right? Because building is now has been brought into a separate part, which we are going to discuss next. And then we have base isolated structures, buildings, pipelines, dams and embankments, coastal structures, steel towers, tunnels, and we can keep on adding more and more type of structures as we move forward as the need arises. So that is the whole strategy. So that is where we get the elastic force, and now from there we know in seismic design we also use R factor to reduce the elastic force to a design force level. So again, the R factor now will be coming from the respective parts for depending on the type of structure and the type of structural system that will be permitted, along with the design and detailing specifications for that particular type of structural system for that type of structure from the 13920 vertical. Right? So 13920 vertical will give the specifications for design and detail. The corresponding value, for those systems, the R factors will be provided in the corresponding part of 1893. So that is how we get this. That is your strength design. Now, of course, we also talk about serviceability. Here again, what happens is serviceability is basically for a lower level of shaking. It's not for that same level of earthquake shaking for which this strength is going to be designed for. So we have that. So that is where you will see EED means strength design and EES means serviceability level earthquake, which is going to be a lower level of earthquake shaking. That's the first part. The second important thing that you must note here that in the load combinations, we do not have anymore a load factor of 1.5 or 1.2 and so on and so forth associated with the earthquake load. Why? Because, and we are going to discuss that in detail, next. But essentially, you can say that today, after doing this hazard analysis, we have confidence on our hazard estimate. We have confidence, much more confidence on our Z values that we are considering, and therefore, there is little need for an additional factor to come in and say that, okay, this load factor is to, partial load factor is to take care of uncertainty in that. All the uncertainties, everything has already been taken care of. So we are not going to have an additional 1.5 load factor, 1.2 load factor and so on. So that's another important thing to know. The next important part, very important concept we need to remember is that we are going to talk about soil flexibility in a more conscious way henceforth, right? In buildings, we have not been talking about, we have these empirical expressions given to estimate natural period. But if you remember bridge code, it says apply, model everything, apply a load and find out what is the displacement. So essentially, particularly in those situations, the flexibility of soil does significantly alter the natural period of a structure. And here the emphasis is to bring in flexibility. Now this is not to be confused or interpreted as the code requires soil structure interaction study to be carried out. No, it is not that. So as a first step, the only thing that we intend to account for is the flexibility part, not the inertia part of the soil, not the inertia of interaction between soil and structure. It is only the flexibility part that needs to come in. So, and then for, because we have a static equivalent linear static method and dynamic method, there is a whole geotechnical group which is looking at all these things in little more detail. Numbers will be finalized, but essentially the idea is to consider soil flexibility and then have appropriate factor of safety for design of foundations and foundation systems. In future, where are we heading? And we'll understand this when we finally close the loop with discussion on IS 456. Today we, as designers, we start with our design stress strain curve of concrete, steel, whatever we have. We come up with a cross section, we do the design, sizing, steel, we do the detailing, and we create members. We finish the detailing, and that is it. After this, we stop, right? Once the detailing is done, drawing is prepared, it is sent, it is constructed, but what is going to be the actual behavior of that particular element, what is going to be the behavior of that structure, is something we believe that by following all the specifications in the standards, my structure will do good. Right? It is the responsibility of the codes and the standards to give us a process that will ensure that everything is good, will be okay. So we really do not check actually what is the behavior of the structure. Now, remember I spoke about the third vertical of assessment. Assessment is essentially where we actually need to understand this, right? Where is the deficiency, what is the behavior, if the behavior acceptable, adequate or not, and so eventually in the long run, I'm not saying today, tomorrow, but in the long run, we need to have a process which is going to be a closed loop. And just like any other design, even a design is iterative in process, this process also has to be iterative. I mean, there is no doubt about it. There is nothing to fear about, right? But then, as a structural engineer, what it will lead to is that we will know exactly what's going to be the behavior. And this is where, I know many of you are talking about performance-based design and things like that in future, right? I mean, if the moment you talk about performance, you have to know what is that performance. And if that performance is not adequate, then obviously we'll go back and redo, tweak something, change something so that you get the desired performance. So that process is something that we aspire to bring in future. I'm not saying it's going to happen overnight. So earthquake resistant design, from that perspective has evolved from the earlier basically stiffness based design, very large systems, to strength based design where even 20 years back it was purely force based. So code gave a force, we did the same analysis and finished it off, probably a little bit of a detailing, right? We thought detailing alone is going to make earthquake resistant structures. Then capacity based design is something that was brought in a big way in the 2016 versions. It was already there in the for instance, IS 13920, 1993, already had capacity design, but we never called it that way. We said detailing alone is going to give us earthquake resistant structures, because the title was actually detailing, earthquake detailing. But if you see 2016 version, the title of that standard changed from design and detail. So that is the capacity design portion, and you are going to see that in a big way. In future, when you talk about load deformation, until now we are sticking to load, but when you talk about load deformation, we are going to talk about deformation-based design, and finally, a robust earthquake-resistant design in terms of energy base. So that will happen in the future, and that is where we should be able to see and predict the entire load deformation characteristics of a structure, wherein we will be able to, we should first ensure good configuration, stiffness, strength, and ductility capacity, of course along with desired mechanisms and collapse mechanism and energy dissipation capacity. That's the overall big picture that we are aspiring to have. And as a first step, of course, we need to start with the right estimate of hazard, and that is what we are doing. But that's not enough. There will be surprises and situations like this, and that is where it's not just structural design, but geotechnical aspects also become an important role in earthquake-resistant design. Today, when we talk about performance and other things, of course, safety not just of the structure, but also of the architectural elements and utilities of a structure have become very important, because our buildings, our structures are becoming more costlier, because not just because of the structural elements cost, but because of all these elements in the structure. So it becomes an important aspect. So this first part I'm going to close here by saying that there is one major change that is happening in IS 1893.